The universe was once dark, so dark that even the idea of light had not yet been invented. No stars and no galaxies, only a quiet, expanding ocean of hydrogen and helium cooling slowly in the silence of cosmic night. And yet, hidden inside that darkness was a faint tension, a gentle imbalance written into the earliest moments of creation, the first clues that gravity would someday weave atoms into fire. Tonight, we drift into that age before starlight, a time when the cosmos was young, weightless, and waiting. A time when the first stars, those ancient beacons that shaped everything after, had not yet been born. What created them? What broke the endless night? And how did the universe take its first luminous breath? Before we begin this quiet journey, if you're kind enough, a gentle like or a soft tap on subscribe would mean more than you know. Your presence here keeps these calm explorations alive, and I'm deeply grateful you're sharing this moment of stillness with me. Now, we drift into part 1. Part 1. What did the universe look like before light? Before the first stars formed, the universe was a silent ocean of cooling gas, smooth, shadowed, and almost perfectly uniform. If you could drift through it, you wouldn't see galaxies or clusters or even a single bright spark. Instead, you'd float through a vast cosmic fog where atoms wandered freely and gravity had only just begun to gather them into the faintest hints of structure. If you could place yourself inside this early cosmos, you would discover a darkness unlike anything your eyes have ever known. Not the darkness of night, which is filled with starlight scattered from distant horizons, but a deeper, more ancient absence of illumination. Here, light had not yet been invented. Hydrogen and helium filled all of space in a quiet, even mist, cooling from the immense heat of the Big Bang. The temperature had fallen far below the blistering incandescent glow of the early universe. And now, everything waited, expanding gently, cooling slowly, drifting without direction except the pull of gravity itself. This period is known to astronomers as the Cosmic Dark Ages. It began roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons to join with protons and form neutral atoms. Before that moment, light could not travel freely. The universe was an opaque plasma, glowing with trapped radiation. But once atoms formed, the fog cleared, and light finally escaped. The faint afterglow of that release is what we now call the cosmic microwave background. It is the oldest light we can see, a stretched, whispering remnant from a universe still in its infancy. But after this release of primordial light, the cosmos dimmed. The glow faded into infrared shadows, stretched by expansion until nothing remained that the human eye could ever perceive. The universe did not grow brighter after that moment. It grew darker, and in that darkness, matter drifted quietly, gathering so slowly that even millions of years passed without a single flame rising. If you were to move through this space, you wouldn't feel motion. Everything around you expanded uniformly, as though space itself were gently pulling you outward. There were no stars to mark direction, no galaxies to draw the eye. Even time felt different, loose, unanchored, without the rhythm imposed by stellar cycles or planetary shadows. The universe had not yet built clocks. It had not yet sculpted anything sharp or bright. It existed in a state of quiet equilibrium. Yet, this stillness was an illusion. Beneath the uniformity, tiny imperfections disturbed the balance. These perturbations, minute ripples in density left over from the earliest instance of cosmic inflation, were the first seeds of structure. Some regions had slightly more matter than others, slightly more gravity, slightly more potential, and over immense stretches of time, these tiny differences would become everything: stars, planets, galaxies, clusters, and eventually the atoms in your own body. But in this early age, their influence was subtle. Gravity moved slowly, pulling gas inward at a pace almost too gentle to measure. If you could float there, watching these ripples evolve, you would see nothing at first. Only patient drifting. Only a quiet dance of atoms cooling and separating as the universe expanded. The earliest clouds of gas were enormous, spanning light years, yet they remained diffuse, delicate, easily disrupted by expansion's pull. It is hard to imagine how empty this universe truly was. The density of matter just after recombination was only a few hundred hydrogen atoms per cubic meter, far more than today, but unimaginably thin compared to any environment we know. For comparison, a room on Earth contains something like 10 trillion molecules in each cubic meter. The early universe was practically a vacuum, a vast cosmic emptiness littered with isolated atoms floating in the dim glow of a fading microwave afterlight. As the universe grew older, temperatures continued to fall. The gas cooled from thousands of degrees to hundreds, then into the tens. This quiet cooling shifted the behavior of atoms. They moved more slowly, collided less frequently, and gathered with a little more willingness. Still, for tens of millions of years, the universe slept in perfect darkness, the silence broken only by the slow murmur of gravitational attraction. If you could listen deeply, not with ears but with an intuition for motion, you might sense the first structures emerging. You might feel their presence as faint gravitational wells where gas accumulated a little more densely. These regions were the earliest halos of dark matter, invisible scaffolding that shaped the formation of everything that followed. Dark matter dominated the mass of the cosmos, quietly pulling normal gas toward its growing clumps. Without it, the first stars would have taken far longer to form, or perhaps not formed at all. Even so, the gas resisted collapse. Pressure pushed outward, expansion stretched space, gravity pulled inward with patient persistence. The balance between these forces created a universe that was stable, calm, and deeply still. Imagine drifting through such a place. The temperature around you might be just a few dozen degrees above absolute zero, the ambient radiation faint and ancient, the atoms sparse but ever present. There was nothing to cast a shadow, nothing to ignite, nothing to glow. And yet, this was the most formative era in cosmic history. The darkness was the canvas upon which all future light would be painted. Every atom drifting in this early universe would someday find a home, inside a star, inside a planet, inside a living cell. The calm that filled this ancient space was not emptiness, it was potential, waiting for gravity to sculpt the first fire. As the dark ages continued, density ripples grew. Regions with slightly more matter became gravitationally unstable, drawing in more and more gas. These pockets deepened slowly, becoming the earliest cosmic clouds, cold, immense, and fragile. They would eventually collapse under their own weight. But in this early stage, they were simply shadows within shadows, hints of future brilliance. If you floated near one of these forming structures, you would feel nothing. No wind, no brightness, no heat. But slowly, over tens of millions of years, the gas inside such a cloud began to compress. The temperature rose imperceptibly. Molecules collided more often. Gravity strengthened as more mass accumulated. A quiet tension grew in the center of each collapsing region. The universe was preparing to light its first candle. But still, for a long time, darkness reigned. Hundreds of millions of years passed before the first stars ignited. During that time, the cosmos grew increasingly structured. Filaments of dark matter stretched across space, threading gas along invisible lines. Voids expanded between them, vast, empty bubbles where little matter ever gathered. By the time the first stars finally formed, the universe had changed profoundly. It was colder, larger, more organized. What began as a smooth ocean had grown into a shifting web of potential, sculpted by gravity's delicate hand. And when one of those dense clouds finally compressed enough, when its center grew hot enough, when pressure and temperature crossed the critical threshold, the dark universe opened its eyes. In that instant, light returned for the first time since the cosmic dawn. The age of stars had begun. But before that moment, before ignition, before brilliance, before galaxies drew their spirals across space, the universe existed in a state of profound peaceful shadow, a darkness that was not empty, but waiting. And as we continue this quiet journey, one question rises gently from that ancient stillness. Why did darkness last so long? Part 2. Why did darkness last? For millions of years. For nearly 200 million years after the Big Bang, nothing in the universe could shine. Atoms were still too warm, too spread out, too gently moving to collapse. Gravity pulled patiently, but the gas resisted, expanding with the universe's breath. This slow tug of war delayed the first light, stretching the darkness across cosmic time. To understand why the universe remained dark for so long, we have to step quietly into an era where everything was changing, yet nothing appeared to happen. The expansion that began in the first instant after the Big Bang did not stop. It slowed, but it continued pushing galaxies that did not yet exist farther and farther apart. Space itself was stretching, and as it stretched, it cooled. But the cooling was slow, steady, meditative, like a long exhale across the fabric of reality. It would take hundreds of millions of years before the temperatures fell to a point where gravity could finally win its first victory. If you imagine drifting through this ancient universe, you would feel no turbulence, no warmth, no light. You would sense only the faint whisper of hydrogen and helium atoms drifting apart, their motions guided by nothing but inertia and cosmic expansion. The temperature of the universe fell from thousands of degrees to just a few dozen over millions of years. But cooling alone was not enough. The gas had to gather, compress, and reach extraordinary densities to ignite the first stars, and the universe was unwilling to allow that, at least not yet. The problem was density. Right after recombination, when electrons and protons finally combined into neutral atoms, matter spread out almost perfectly evenly across space, too evenly. Gravity, though patient, needs contrast, regions slightly more massive than others. But the early universe was too smooth. The density ripples left over from cosmic inflation were incredibly faint, only 1 part in 100,000. These tiny differences were seeds of structure, but in the beginning, they were too gentle to make matter clump quickly. So gravity began its long, slow negotiation with the expanding cosmos. In the densest regions, its pull strengthened, drawing atoms inward. But in the vastness between them, space itself expanded more rapidly, whisking matter away before it had a chance to gather. This constant push and pull created a delicate balance, one that favored expansion for millions of years. The universe had unlocked transparency. It was no longer a glowing plasma, but it had not yet learned how to generate light of its own. During this era, known as the Cosmic Dark Ages, nothing truly dramatic occurred from the perspective of the eye. But from the perspective of physics, everything was evolving. Hydrogen began to cool enough for molecules to form, tiny pairs of hydrogen atoms, fragile but essential. These molecules helped radiate away heat, allowing gas clouds to collapse more easily. But this process was slow, and molecular hydrogen was rare. The early universe lacked dust, metals, or complex chemistry. All the ingredients that help gas cool today were missing back then. Even so, dark matter was hard at work. Invisible halos of dark matter, vast, diffuse structures, had begun to form under the influence of gravity's pull. These halos did not emit light, but they supplied the gravitational wells that normal matter would eventually fall into. Without dark matter, the formation of the first stars might have taken billions of years instead of hundreds of millions. But even with its assistance, the gas inside these halos remained too warm, too energized to collapse quickly. When we imagine star formation, we often picture a cloud of gas collapsing suddenly under gravity's pull. But nothing about the early universe was sudden. Every change required time on a scale almost impossible to comprehend. 10 million years, 50 million, 100. And through all these epochs, the darkness persisted, unwavering. Even the background light left over from the Big Bang was fading, stretched by cosmic expansion into a cold microwave whisper that no longer illuminated anything. If you could watch this era unfold in time-lapse, you would finally begin to see subtle hints of structure. Small, overdense regions, the tiniest clumps, began to grow. Gas slowly spiraled inward, its pressure rising. The temperature increased in these regions, but not enough to ignite fusion. Instead, the gas resisted, pushing outward. Collapse slowed, gravity pulled further. This rhythmic tension defined the Dark Ages. The universe was learning to compress, but it had not yet accumulated enough mass in one place to spark nuclear fire. Meanwhile, outside these forming structures, most of the universe remained almost perfectly empty. The density of matter was so low that a single cubic meter of space might contain only a few atoms. For gravity, this emptiness was a challenge, and so the contraction of gas clouds became a story of persistence, atoms falling inward by the faintest fraction more than they drifted apart. A slow gathering, barely perceptible moment to moment, but monumental over cosmic time. At around 100 million years after the Big Bang, gravity began to gain ground. Dark matter halos deepened, gas cooled further, collisions among atoms grew more frequent in the densest pockets. The earliest hints of rotation emerged as clouds twisted subtly under the influence of tidal forces. These clouds grew denser, heavier, and more unstable. But they still resisted collapse. They were not yet ready. Only when the universe approached 150 to 180 million years old did the conditions finally tip. In the largest halos, those weighing millions of times more than the Sun, gas clouds had grown massive enough that gravity overwhelmed pressure. At last, collapse accelerated. Gas fell inward faster than expansion could counter. Temperatures climbed, density rose. The cores of these clouds brightened with invisible heat. And yet from the outside, nothing changed. The universe was still silent, still dark. But deep within the collapsing clouds, something extraordinary was about to occur. As temperatures neared 10,000 degrees, molecular hydrogen cooled the gas more efficiently. These early clouds fractured into smaller clumps, each potentially birthing a star. In the centers of the densest clumps, temperatures climbed further, reaching hundreds of thousands of degrees. Pressure surged. The atoms inside were squeezed together so tightly that quantum effects began to influence their behavior. Then came the final stage, gravitational freefall. When the core density reached a critical threshold, collapse accelerated dramatically. Heat soared into the millions of degrees. And at those temperatures, after nearly 200 million years of darkness, hydrogen atoms finally began to fuse. Light had returned to the universe. The first stars were unlike anything that exists today. Their masses were enormous, hundreds of times the mass of the Sun. They burned fiercely, brilliantly, and briefly. But before they ignited, before they radiated ultraviolet light that would ionize the universe and carve away the cosmic fog, there was that long silence. A silence in which gravity learned how to overcome expansion, how to cool gas, how to sculpt the universe into the structures that would someday shine with starlight. Darkness was not a mistake. It was preparation, the quiet interval needed for matter to gather, organize, and deepen. And as we continue drifting through this ancient story, another question takes shape gently from the vastness. What forces begin the birth of a star? Part 3. What forces begin the birth of a star? A star begins not with fire, but with falling, hydrogen and helium drifting inward under gravity's pull. As pockets of gas grew heavier, they collapsed into themselves, compressing, heating, and tightening until their centers warmed with quiet fury. Deep inside these collapsing clouds rested a simple truth. Pressure and gravity were on a slow, inevitable path toward ignition. If you could watch this process unfold, not in minutes or hours, but over millions of years, you'd see that the earliest stages of a star resemble a long, silent inhale of the universe itself. Gas does not rush inward. It drifts, it gathers. Its motion is guided by the invisible arms of gravity, stretching across light years and pulling atoms toward one another with infinite patience. In these early moments, the cloud remains cold and dim, its shape dictated only by the interplay of density, temperature, and the faint fingerprints of turbulence born long before its collapse began. This collapsing cloud is known as a molecular cloud, though in the primordial universe, it was simpler. Mostly hydrogen, a little helium, and just the faintest whisper of molecular bonds. These clouds were enormous, spanning tens or even hundreds of light years. Yet, despite their size, they were astonishingly diffuse. If you placed your hand inside one, you would feel nothing. No wind, no warmth, only a few stray atoms brushing gently past your skin. And yet these sparse atoms held the future of countless stars. The collapse begins when the balance between pressure and gravity tilts just slightly toward gravitational attraction. Pressure, pushes outward, resisting compression. Gravity pulls inward, encouraging it. For a cloud to collapse, gravity must gain even the smallest advantage. In the early universe, this advantage emerged when the densest regions, those formed by tiny fluctuations in matter after the Big Bang, became just heavy enough to overcome their internal support. Once gravity took the lead, the cloud began to contract. Slowly at first, almost imperceptibly. But as atoms drifted inward, they collided more frequently. Every collision converted a bit of gravitational energy into heat. The center warmed. The outer layers drifted inward with increasing momentum. But this collapsing motion did not occur as a uniform squeeze. Instead, the cloud's interior fractured into smaller knots, regions where gravity tugged more strongly. These knots became the birthplaces of individual stars. If you hovered near one of these forming protostars, you would feel the gentle tension of gravity pulling everything toward the core. The temperature would rise as you drifted closer. At first, just a few degrees above the frigid background of space, then hundreds, then thousands. Density increased. Atoms that had spent millions of years wandering freely were suddenly locked into a tightening embrace. But collapse alone isn't enough to make a star. The gas must not only fall, it must cool. Without cooling, the pressure from rising temperatures would halt collapse prematurely, leaving behind a warm, diffuse sphere that never ignites. In the modern universe, cooling is aided by dust, metals, and complex molecules. But in the primordial universe, cooling depended almost entirely on molecular hydrogen, rare, fragile pairs of hydrogen atoms that could radiate away heat. As cooling continued, collapse accelerated. The cloud contracted further. Its central region grew dense enough to create a distinct object, a protostar. From the outside, this protostar was dark, hidden inside layers of dust and gas. But inside, pressure and temperature continued to climb. Gravity squeezed the core with relentless force, and every atom that fell inward contributed to the rising heat. Yet the core remained silent. Fusion had not begun. Not yet. This stage of stellar birth is known as free-fall collapse, and it lasts until the cloud's internal pressure begins to resist gravity's pull. When that moment arrives, the collapse slows. The protostar enters a state of hydrostatic balance, a temporary calm where the inward pull of gravity matches the outward push of pressure. This balance is fragile. Any slight imbalance will cause collapse to resume or pressure to rise further. During this phase, the protostar begins to spin. Angular momentum, the conserved motion inherited from the cloud's earliest turbulence, causes the collapsing gas to rotate faster as it contracts, much like a figure skater drawing in their arms. This spin flattens the surrounding gas into a disk, an elegant, thin structure orbiting the newborn star. In this disk, future planets will someday form. But for now, the disk's main role is to feed material into the growing core, adding mass and increasing temperature over time. If you could see inside the protostar, you would witness a rising tide of heat. At 10,000 degrees, the gas glows faintly. At 100,000, hydrogen becomes ionized. At 1,000,000 degrees, the core begins to press atoms together with such intensity that their electrons are stripped away completely. And yet, fusion still eludes the protostar. The conditions must be perfect. The core must reach temperatures exceeding 10 million degrees. Pressure must be immense, and density must be high enough to force hydrogen nuclei to fuse despite their mutual repulsion. All the while, gravity continues to pull inward. Each atom joining the core adds to the weight pressing down on its center. Each addition raises the temperature. Each rise brings the protostar closer to ignition. And in these moments, a delicate interplay begins to shape the star's fate. If the protostar accumulates enough mass, its core will ignite. If not, it will fade into a brown dwarf, a failed star glowing faintly with the heat of its collapse. But for the first stars, ignition was inevitable. Their birth clouds were so massive that they gathered hundreds of solar masses before collapse slowed. In these giants, the core was squeezed with unimaginable force. Temperatures soared past 10 million degrees, then 15, then 20. At these temperatures, nuclear fusion begins. Hydrogen nuclei fuse to form helium, releasing energy. This energy pushes outward, counteracting gravity, creating the delicate equilibrium that defines a star. The moment fusion begins, the protostar becomes a true star. Light escapes from the core, filtered through layers of gas. The darkness breaks, the universe brightens, and a new point of light emerges where none existed before. But the journey to ignition is more than physics. It is a transition from collapse to balance, from falling to burning, from darkness to illumination. Gravity, pressure, cooling, rotation, all of these forces shape the birth of a star, guiding it from a drifting cloud of gas into a luminous engine of nuclear fire. A star is not created suddenly. It is sculpted slowly, patiently, through forces that act in silence and over immense stretches of time. It is the universe learning to light itself. And as we drift deeper into this cosmic story, one question naturally rises from the heart of this transformation. How did tiny imperfections shape everything that followed? Part 4. How did tiny imperfections shape everything? The first stars were born from flaws, minute density ripples left over from the universe's birth. These ripples, only millionths of a degree in temperature difference, guided gravity like faint fingerprints. What looked like almost perfect smoothness hid the seeds that would someday become galaxies, clusters, and the fiery hearts of the very first stars. If you could drift through the universe in its earliest ages, you might believe at first that space was perfectly uniform. Hydrogen and helium stretched in every direction with almost no variation, bathed in the dim, fading glow of the cosmic microwave background. And yet, hidden within that smoothness were tiny imbalances, small pockets where matter was faintly more concentrated than its surroundings. These regions were not visible, not even in principle. There was no light to reveal them. But mathematically, physically, gravitationally, they were everything. These imperfections arose from quantum fluctuations, tiny, unpredictable jitters in energy that occurred when the entire observable universe was smaller than a grain of sand. During the earliest fraction of a second after the Big Bang, cosmic inflation expanded space faster than light, stretching these fluctuations across vast scales. What began as subatomic variations were blown up into cosmic ripples, patterns etched permanently into the structure of the universe. They were impossibly small in amplitude, but perfectly positioned to shape everything that would ever form. When the universe cooled enough for atoms to appear, these ripples became tiny variations in density and temperature. Where the density was slightly higher, gravity was slightly stronger. Where it was slightly lower, gravity was slightly weaker. No drama, no sudden motion, just the faint tug of a slightly more massive region of space, an almost imperceptible pull that would define the future of galaxies. Over millions of years, these tiny overdense regions began to grow. They did so not because gravity acted with sudden force, but because the universe expanded around them. As space expanded, matter thinned, but the overdense pockets thinned a little less. Their relative density increased, and slowly, gravity's influence strengthened, gathering nearby gas more effectively than their surroundings could. If you could hover near one of these ripples and watch, you wouldn't see motion you could track with your eyes. You would sense a slow migration of atoms, drifting gently toward a slightly deeper gravitational well. Expansion still fought back, stretching space and pulling gas outward. But inside the ripple, gravity held its ground. It was like a shallow basin in an otherwise flat floor. Most marbles roll away, but a few drift toward the slightly lower center. In this way, structure grew in silence. These earliest fluctuations formed a pattern, a cosmic web of filaments and voids. Regions where dark matter pooled more densely created the threads of this web. Regions where matter was scarce became vast, empty voids. The early universe, though still dark and uniform to the human imagination, was already partitioning itself into the architecture that would support galaxies. These filaments of dark matter acted as invisible scaffolding, shaping the distribution of normal matter that followed their pull. As gas collected in these filaments, the densest intersections gradually became halos, regions where gravity grew strong enough to slow expansion locally. These halos were not yet galaxies. They were faint concentrations of matter, the earliest building blocks of cosmic structure. Each halo held the promise of a future star or cluster of stars, and each one existed only because of a slight imperfection, a deviation in density so small that it lay far below our sensory intuition, but deeply embedded in the mathematics of the universe. The imperfections also revealed themselves in the cosmic microwave background, the afterglow of the Big Bang. Satellites like COBE, WMAP, and Planck captured temperature fluctuations in this glow with extraordinary precision. Some were only a few millionths of a degree above or below average. Yet these minute variations represent the seeds of all cosmic structure. The peaks correspond to overdense regions, the troughs to underdense ones. When scientists map these fluctuations, they are essentially seeing the blueprint of the universe's future, where galaxies will form, where voids will open, where clusters will rise. It is astonishing that the universe's grandest structures, the spiraling arms of galaxies, the towering walls of galaxy clusters, the vast emptiness of cosmic voids, all trace their origins to quantum-scale fluctuations magnified by cosmic inflation. In the deepest sense, the universe as we know it is a fossil record of randomness sculpted by physics. But these imperfections did not merely shape structure, they shaped timing. Regions with slightly higher density collapsed earlier, creating the first stars. Regions with lower density took longer to form anything at all. This difference meant that the universe did not ignite uniformly. Instead, the first stars formed in isolated pockets, separated by great expanses of darkness. These stars lit their surroundings with ultraviolet radiation, carving bubbles of ionized gas that expanded over time. But there were still vast regions untouched by light, still waiting for their density ripples to grow strong enough to collapse. This uneven arrival of starlight is why the universe experienced a dawn rather than a sudden flood of illumination. Light reappeared in patches, slowly spreading outward, overlapping, merging, and eventually reionizing the entire cosmos. But that process, too, traces back to the tiny imperfections that dictated where the earliest structures would form. Even more remarkable is that these imperfections influenced the types of stars that emerged. In the densest ripples, gas collapsed more quickly, creating more massive protostars. These giants lived short, brilliant lives. In slightly less dense regions, smaller stars were born, destined to live for billions or even trillions of years. A fraction of these first stars may still exist today, ancient survivors of the universe's earliest generations. These imperfections also shaped the distribution of dark matter. Simulations of the early universe show dark matter flowing into the densest fluctuations first, amplifying their gravitational influence. This feedback loop caused overdense regions to grow more rapidly, drawing in even more matter. The result was a hierarchical structure, small halos forming first, merging to create larger ones, and eventually assembling the immense structures we see today. Even now, billions of years later, we can still detect the influence of these primordial fluctuations. The arrangement of galaxies across the cosmos follows the same pattern, clustered along filaments, separated by voids. Every galaxy group, every supercluster, every cosmic void, all reflect the initial imbalances written into the early universe. It is humbling to realize that without these tiny imperfections, nothing we know would exist. A perfectly smooth universe would have remained dark and featureless. Gravity would have no footholds, no structure would form, no stars would shine, no planets, no life, no observers to wonder about any of it. Imperfection is the reason anything happens at all. In the stillness of those early moments, randomness became order. Subatomic fluctuations became galaxies. Chance became destiny. And the smallest variations in temperature, a millionth of a degree's difference, determined where the first stars would ignite and where darkness would linger a little longer. And as we drift from those quiet imperfections toward the flames, they would light. Another question rises gently. Why were the first stars so enormous? Part 5. Why were the first stars so enormous? The earliest stars were nothing like the ones we see today. With no heavier elements to cool the gas, their birth clouds grew colossal. As they collapsed, they formed stars hundreds of times more massive than the Sun. Their lifetimes were brief, their luminosity overwhelming, and their influence on the cosmos impossible to overstate. To understand why these first stars, known as population 3 stars, became such giants, we need to step gently into the physics of the early universe, an era when the rules of star formation were the same as today, yet the ingredients were profoundly different. Everything we now know about star birth, its limits, its cooling pathways, its fragmentation, depends on the chemistry of the gas. And the primordial gas, the gas after the Big Bang, was astonishingly simple: hydrogen, helium, and trace amounts of lithium, nothing more. No carbon, no oxygen, no silicates, ices, or dust, no metals of any kind. This absence was not a trivial detail. It shaped the destiny of the first stars. If you could drift into one of the enormous gas clouds forming in the early universe, you would find them warm, smooth, and slow to collapse. Modern star-forming clouds cool efficiently thanks to dust grains and complex molecules that radiate energy away. But the primordial clouds had only molecular hydrogen, H2, to help them shed heat. And H2, though essential, is a poor coolant. It can only radiate energy at very specific frequencies, making it far less efficient than the tools available to the cosmos today. Inefficient cooling means higher temperatures. Higher temperatures mean greater pressure-resisting collapse. And to overcome that pressure, the cloud needed to grow more massive, far more massive than modern clouds. The earliest star-forming regions were not just hundreds of solar masses, they were tens of thousands. A single collapsing cloud often held enough material to create dozens of massive stars, but instead, it typically fractured into only one or a few colossal protostars. The process played out slowly, like an immense breath being drawn inward. Gas drifted toward the center of each cloud, but without efficient cooling, it could not fragment into smaller clumps. Instead of many tiny knots forming, the cloud collapsed into larger, denser regions. Each region gathered incredible amounts of mass, feeding the growing protostar at its center. And because nothing cooled the gas quickly, accretion continued almost unchecked. If you could watch one of these protostars forming, you would see a disk of gas spiraling inward, thick, hot, and luminous even before nuclear fusion ignited. The protostar would swell to enormous size, hundreds or even 1,000 times the radius of the Sun. Its outer layers, bloated by intense radiation pressure, would pulse gently in the darkness. It would glow faintly with the heat of collapse long before true starlight emerged. Inside, its temperature rose relentlessly. At 10 million degrees, hydrogen fusion began. At 15 million, the energy output increased dramatically. And at 20 million degrees or more, a temperature easily reached in these massive cores, the star's radiation became powerful enough to push back against the inflowing gas. But here lies the crucial difference. The early universe lacked dust. Dust today helps regulate the flow of gas into a forming star. It absorbs radiation, shields parts of the cloud, and prevents the protostar from feeding too rapidly. Without dust, radiation from the forming star passed almost freely outward. It could not halt the inflow of gas as effectively. As a result, massive star formation continued long after fusion began, feeding these giants with fresh hydrogen and helium, making them grow larger and larger. These protostars grew with incredible efficiency. Modern stars typically reach 10, 20, sometimes 50 solar masses before radiation pressure stops the inflow. But for the first stars, the limit was far higher. Many are believed to have reached 200 to 300 solar masses. Some models suggest that in rare cases, they may have approached 500 or even 1,000 solar masses, titans by any modern standard. Their immense size affected everything about their behavior. Massive stars burn hotter because their cores must balance greater gravitational pressure, and burning hotter means burning faster. A star like our Sun lives for around 10 billion years. A 100 solar mass star lives only a few million. A 300 solar mass star might live for just 2 million years or less, a cosmic blink. They came and went so quickly that no living organism would ever witness such a star persist across deep time. But their brilliance during those short lives was extraordinary. Population 3. Stars may have been millions of times more luminous than the Sun. Their ultraviolet radiation carved ionized bubbles in the surrounding gas, stripping electrons from hydrogen and helium, gradually reionizing the universe and ending the cosmic dark ages. In doing so, they transformed the chemical structure of space, creating the first pockets of transparent, illuminated cosmos. And then, when their fuel was spent, they died with violence unlike anything familiar today. Most massive stars today end their lives in supernovae, brilliant explosions that scatter heavy elements across space. But the most massive population 3 stars experienced an even more dramatic fate: pair instability supernovae. At extreme temperatures, high-energy photons can create pairs of electrons and positrons. These pairs reduce radiation pressure in the core, causing it to collapse rapidly before exploding with unprecedented fury. These explosions released more energy than any modern supernova. They completely unbound the star, leaving no remnant behind, not even a black hole. The explosion scattered heavy elements throughout the gas clouds, enriching the universe with carbon, oxygen, nitrogen, silicon, and iron for the first time. The earliest simple molecules, water, carbon monoxide, methane, could only form after these elements appeared. Planets could only form after dust grains existed. Life, at least as we know it, required these elements scattered by the deaths of colossal stars. In this way, the first stars were both creators and destroyers. Their brilliance reionized the universe, their deaths rewrote its chemistry, and their massive size ensured that this transformation happened quickly, seeding the cosmos with everything necessary for future generations of stars. When astronomers look at distant galaxies with the James Webb Space Telescope, they catch subtle hints of these ancient giants, galaxies glowing too brightly, too early, filled with stars that seem impossibly hot. We cannot see the first stars directly, but we see their fingerprints: ionized gas, unusual spectral signatures, and patterns of early chemical enrichment that can only come from massive stellar ancestors. It's remarkable to think that the enormous size of the first stars was not a coincidence, but a consequence of cosmic simplicity. The universe without metals was a universe destined to create giants, and as we drift forward from their luminous, short-lived brilliance, one question naturally emerges: what sparked the first nuclear fire that made them shine? Part 6. What sparked the first nuclear fire? At the core of each collapsing cloud, temperature and pressure climbed quietly upward. When the heat reached nearly 10 million degrees, something extraordinary happened. Hydrogen atoms fused, releasing energy that pushed back against gravity. In that moment, the universe produced its very first light. A star had awakened. To understand what ignited that first flame, we must drift inward, deep inside the heart of a collapsing protostar, a place where darkness grows warmer, denser, and more restless with every passing moment. From the outside, everything still appears quiet. The cloud remains wrapped in its cocoon of cold, neutral gas. No light escapes, no signature marks the forming core. But inside, the laws of physics are gathering momentum. Gravity, patient until now, begins to assert its full authority. As the gas contracts, gravitational potential energy transforms into heat. Every falling atom, every collision adds a whisper of warmth to the core. These whispers accumulate, merging into a rising tide of thermal energy. But the path toward ignition is slow. Even when the temperature reaches thousands of degrees, fusion does not begin. The atoms simply move faster, collide harder, and crowd closer. The protostar remains dark. Pressure, however, begins to build. The weight of all the overlying gas compresses the core, forcing particles into a smaller and smaller space. This pressure is not a force you could see or feel directly. It is a consequence of density, a quiet, relentless squeezing caused by billions of atoms vying for the same volume. Gravity is pushing inward, thermal motion is pushing outward, and the core is caught between these opposing arms, trapped in a delicate tension. The key to nuclear ignition lies in overcoming the electric repulsion between hydrogen nuclei. Each nucleus carries a positive charge. Positive charges repel each other. To fuse, they must be forced so closely together that the strong nuclear force, the most powerful force in nature, can bind them. But this binding occurs only at unimaginably close distances, distances so small that even the atoms themselves do not naturally encounter them. To bridge that gap, the temperature must rise, not slightly, not modestly, but dramatically. At around 10 million degrees, the motion of hydrogen nuclei becomes fast enough that collisions occasionally overcome their repulsive barrier. When two nuclei meet at such speeds, they can slip past their electric defenses and merge. When they merge, they release energy, pure, radiant nuclear fire. That first spark did not produce a blazing light visible across the cosmos. At first, the ignition is subtle, deep within the core, where photons are trapped and scattered thousands of times before escaping. But the fusion marks a turning point. Gravity no longer reigns unchecked. For the first time, outward pressure from nuclear fusion begins to balance inward gravitational collapse. A state of hydrostatic equilibrium forms, the defining characteristic of a stable burning star. But fusion is not an instantaneous switch. It begins slowly, like embers forming in a bed of charcoal. The simplest reaction, the proton-proton chain, is extraordinarily slow. A hydrogen nucleus may wait billions of years for a fusion event, yet the number of nuclei is so vast and the core temperature so high that fusion becomes stable and self-sustaining. The first stars, however, did not rely solely on gentle reaction chains. Their massive cores burned with ferocity. Temperatures soared beyond the minimum threshold, reaching tens of millions of degrees. At these extremes, additional fusion pathways opened. The carbon-nitrogen-oxygen cycle, an alternate chain of reactions, could accelerate the rate of fusion dramatically. But this cycle required carbon, nitrogen, and oxygen, and the early universe had none. So the first stars relied entirely on the proton-proton chain, a slow but steady process that delivered extraordinary power simply because the stars were enormous beyond anything we see today. Once fusion became stable, the protostar transformed into a main sequence star. Pressure from the hot core pushed outward, gravity pulled inward. The balance created a state of luminous equilibrium. This balance is astonishingly precise. If fusion rates increase, the core expands slightly, cooling the fusion reaction. If fusion decreases, the core contracts, heating the gas and reigniting fusion. In this way, a star regulates itself with the same calm rhythm as a beating heart. But for the first stars, this balance occurred at extreme scales. Their cores were not modest furnaces. They were superheated, crushing chambers where fusion proceeded with astonishing efficiency. The sheer mass of these protostars allowed their cores to reach temperatures far above the sun's. Some may have burned hydrogen at 50 million degrees or more. As their cores heated, their luminosity soared, increasing exponentially with mass. This luminosity did more than shine. It shaped the surrounding universe. The ultraviolet radiation released in the first moments of fusion began to ionize the surrounding gas. Electrons were stripped from atoms. The dark clouds that once fed the star became carved into hollow cavities of transparent, glowing hydrogen. These cavities expanded outward, marking the earliest sculpting of the interstellar medium. The dark universe began to fracture. Meanwhile, deep inside the core, fusion left its signatures. Hydrogen turned into helium nuclei, sometimes fused into beryllium and carbon. Tiny quantities of heavier elements emerged as the star aged. These early traces of metals would influence later generations of stars, making them smaller and more complex than their ancestors. But for now, the first stars were pure engines of hydrogen fusion, simple, colossal, and incandescent. The ignition of the first stars marked the end of the cosmic dark ages. Light returned to the universe, not sunlight, not starlight as we know it, but a fierce ultraviolet blaze that traveled through space with enough energy to alter the chemistry of the cosmos. From these first flickers, the universe began a transformation that would eventually allow galaxies, planets, and life itself to emerge. The process of ignition also marked the beginning of chemical evolution. Each fusion event released not only energy, but also the building blocks of future chemistry. The first stars would go on to forge heavier elements in their cores: carbon, oxygen, nitrogen, the essentials of planets and living systems. But none of that could happen until hydrogen first fused. Fusion is the gateway, the threshold between collapse and creation. The moment when gravity's inward pull meets its luminous counterpart. The moment when a star stops falling and starts burning. If you could witness the first spark, you would not see a flame. You would feel a sudden equilibrium, the collapse slowing, the core stabilizing, the star finding its balance. And though the outer layers remain opaque, the core is now bright enough to outshine entire galaxies. In that quiet, incandescent moment, the universe awakens to its own brilliance. And as the first stars begin to shine, another question naturally rises. How did these stars reshape the darkness around them, transforming a silent universe into one filled with light? Part 7. How did the first stars transform the dark universe? Once the first stars lit, the darkness began to fracture. Their ultraviolet light traveled outward, stripping electrons from surrounding atoms and creating growing bubbles of transparent space. Slowly, the fog of the early universe thinned, allowing light to pass freely for the first time in cosmic history. To understand this transformation, imagine drifting through the universe just before the first stars ignited. The cosmos was filled with a cold, neutral fog, hydrogen atoms with their electrons intact, drifting in an almost perfect darkness. This fog wasn't thick in the way mist feels on Earth. It was unimaginably thin, almost a vacuum. But its presence mattered. Neutral hydrogen absorbs light, especially high-energy photons. Even if a star had existed in that darkness, its light would have struggled to travel far. The universe was transparent only to the longest wavelengths, and nearly opaque to the radiation that stars would soon begin to release. But then, one star formed, then another, then dozens more, hidden inside the densest regions of primordial gas, each one ignited with temperatures and luminosities far beyond those of most stars today. These were cosmic beacons, massive hot stars blasting ultraviolet light in all directions. Their radiation met the surrounding hydrogen fog and initiated a quiet, profound change. Ultraviolet photons carried enough energy to strip electrons from hydrogen atoms, turning them into charged particles. And once the atoms were ionized, the fog became transparent. The universe began a process known as reionization, a sweeping transformation that turned an opaque cosmos into one that light could finally traverse. If you could drift near one of these first stars, you would see the effects of their radiation not as bright illumination. The fog still obscured that, but as expanding bubbles where the gas became ionized. These bubbles were like cosmic lanterns, not glowing with visible light but made transparent by the absence of electrons. Inside each bubble, the universe was finally clear. Outside, it remained shrouded in neutral gas as dark as ever. The bubbles grew over millions of years, merging gradually like widening ripples in a still pond. As more stars ignited, their combined radiation accelerated the clearing process. Regions near clusters of early stars became vast ionized zones, pushing outward into the last remnants of the cosmic fog. But this wasn't a sudden dawn. It was a slow awakening. The universe brightened unevenly, patch by patch, driven by the distribution of the earliest stars. In these illuminated pockets, the chemistry of the universe began to shift as well. The energy from ultraviolet radiation broke molecular bonds, preventing the formation of fragile molecules like hydrogen H2, which the first generation of stars had relied upon for cooling. This shift altered the future of star formation. In some regions, the suppressed cooling delayed the creation of new stars. In others, shock waves from stellar winds and radiation pressure compressed gas further away, triggering new waves of starbirth. Light was no longer just a byproduct. It had become a sculptor. The radiation also heated the surrounding gas. In some areas, the temperature rose from a few tens of degrees above absolute zero to thousands. This heating changed the density of the intergalactic medium, making some regions expand faster and others collapse more slowly. The interplay of heated and cooling gas wove new patterns into the cosmic web, influencing where future galaxies would form. But reionization was only one part of the first stars' transformation. Deep inside their cores, these massive stars forged the universe's first heavy elements: carbon, oxygen, nitrogen, and eventually iron. When the first stars died, their supernova scattered these elements into space, enriching the primordial gas with materials that would change everything. The next generation of stars would form more easily, fragmenting into smaller masses thanks to the improved cooling offered by metals. Planets, moons, dust, and complex chemistry would all become possible because of the elements the first stars created and released. In this way, the first stars acted as cosmic alchemists. Their lives were brief, but their influence eternal. Every carbon atom in your body, every oxygen atom you breathe, every calcium atom in your bones emerged from the heart of a star that lived billions of years before the sun existed. The universe began with hydrogen and helium, but it did not remain simple for long. The first stars complicated the cosmos, adding richness, diversity, and potential. Their light also provided feedback, an invisible pressure that shaped young galaxies. Intense radiation pushed gas outward, sweeping it into new forms. Some early galaxies lost much of their gas entirely, stripped bare by their own first stars before they could grow larger. Others, more massive and stable, absorbed the radiation and continued forming stars, using the enriched gas from supernovae to produce a more varied stellar population. Meanwhile, the ionized bubbles grew larger. After a few 100 million years, entire regions of the universe had become transparent. The fog had thinned so thoroughly that light streamed freely across enormous distances. By around 1 billion years after the Big Bang, reionization was largely complete. The darkness that followed recombination, the long cosmic night, was finally over. The universe was no longer a place where light fought to escape. It was a space where light traveled effortlessly, tracing the structures gravity had been building since the earliest fluctuations. If you could look down at this unfolding transformation from some quiet vantage point, it would resemble a slow blooming, blackness giving way to expanding pockets of clarity. The first stars acting as cosmic gardeners, clearing the fog and planting the seeds for galaxies. The reionization era was not uniform. It was complex, patchy, and deeply influenced by the distribution of early matter. But in its complexity, it created the conditions necessary for everything that followed: galaxies brightening, spiral arms forming, clusters condensing, and cosmic order emerging. Today, astronomers observe the remnants of this transformation through the night sky. The distribution of ancient galaxies, the behavior of intergalactic gas, and the faint fingerprints in the cosmic microwave background all reveal the story of reionization. The earliest stars cannot be seen directly, not even with the James Webb Space Telescope, but their effects are written into the universe in patterns of ionized gas and early chemical enrichment. The first stars took a universe filled with darkness, simplicity, and neutrality and transformed it into something transparent, chemically complex, and rich with possibility. Their light didn't just illuminate space, it changed its very nature. Their deaths didn't just end their lives, they began the lives of future stars, future planets, future observers. And as we drift onward along this quiet timeline, another question emerges gently from the ashes of these first stellar explosions. Why did these giants live so fast, and why did they die so young? Part 8. Why did these stars live fast and die young? Massive stars burn fiercely but briefly. In just a few million years, these ancient giants exhausted their nuclear fuel. Their cores collapsed, their outer layers exploded, and their deaths, violent, luminous, and swift, rewrote the chemistry of the universe forever. To understand why the first stars lived such short, intense lives, we need to rest inside the heart of their physics, deep in their cores, where temperatures soared to tens of millions of degrees and nuclear reactions unfolded at breathtaking speeds. Unlike smaller stars, which burn their hydrogen slowly and steadily, Massive stars operate at extremes. Their cores are so hot and so dense that fusion proceeds with a kind of cosmic urgency. The star is constantly fighting gravity, and this struggle shapes everything about how long it can live. A star's lifespan is determined not by the size of its fuel tank, but by how quickly it burns it. And the first stars, known as population 3 stars, burned their fuel with astonishing ferocity. Imagine a campfire the size of a mountain. Its flames would consume wood at a rate far faster than a small hearth fire. In the same way, a massive star consumes hydrogen thousands of times faster than a small one. The force of gravity crushing inward on a giant star is immense. To resist collapse, the star's core must produce enormous amounts of energy. That energy comes from fusion, and when fusion runs at such a high rate, fuel is spent quickly. If you drifted near one of these early giants, you would feel the heat radiating outward even across light years. These stars shone millions of times brighter than our sun. Their light was so powerful that it sculpted the surrounding gas, carving cavities and heating the interstellar medium. But behind this brilliance was a kind of instability. Gravity pressed inward with overwhelming strength, and the only resistance came from the radiation produced by fusion. The star's stability depended on an extremely delicate balance, and that balance was maintained only by burning fuel at a pace that could not be sustained for long. The larger the star, the higher the temperature in its core, and the faster fusion proceeds. A star like our Sun burns hydrogen slowly, converting it into helium over billions of years. But a 200 solar mass star can exhaust the same percentage of its hydrogen in a few million years. Up close, the difference is staggering. The Sun leisurely fuses around 600 million tons of hydrogen each second. A massive population 3 star may have fused tens of billions of tons every second, an unimaginable rate, necessary only because its gravitational burden demanded such immense output. Inside these early Aular giants, fusion followed paths unfamiliar to stars like the Sun. With core temperatures far exceeding those of smaller stars, alternative reaction chains become dominant. The carbon-nitrogen-oxygen cycle, the CNO cycle, can accelerate fusion dramatically. But the very first stars lacked carbon, nitrogen, and oxygen. They began life with only hydrogen and helium, so they relied initially on the proton-proton chain, which is slower, but still powerful at extreme temperatures. As the stars matured and created carbon in their cores, the CNO cycle eventually switched on, accelerating fusion even further and hastening their demise. As hydrogen fuel dwindled in the core, gravity began to gain the upper hand. The core contracted, heating even more until helium fusion began. Helium transformed into carbon, then carbon into oxygen, then oxygen into heavier elements. This process is like climbing a ladder of nuclear reactions, each rung requiring higher temperatures and producing heavier elements. But even these reactions cannot continue forever. At each stage, the star burns through its fuel faster than the stage before. In the heaviest of the first stars, these reactions climbed all the way to iron. And iron is special. When lighter elements fuse into heavier ones, energy is released. But when iron fuses, it absorbs energy. Fusion can no longer support the star against gravity. The core becomes unstable, a trapped, dense mass speeding toward collapse. What happens next is among the most dramatic events in the universe. When the core collapses, it happens in a fraction of a second. The enormous weight of the outer layers falls inward, slamming into the core at a significant fraction of the speed of light. Temperatures spike to billions of degrees. Neutrinos, those ghost-like particles, flood outward in a burst so intense that it can momentarily outshine an entire galaxy. The collapse triggers either a massive supernova or, in the largest of the first stars, a pair instability supernova. Pair instability supernova were unique to the earliest giants. At temperatures above 1 billion degrees, high-energy photons begin producing pairs of electrons and positrons. This reduces the radiation pressure holding up the star, causing the core to contract violently. The contraction triggers runaway fusion reactions that tear the star apart entirely. No core remains, no black hole forms. The explosion is complete. scattering the heavy elements the star created across vast distances. These explosions were not just bright, they were transformative. They seeded the interstellar medium with the first metals: carbon for life, oxygen for water, silicon for rock. The dust and heavy elements that now fill galaxies trace their origins back to these moments. Without these violent ends, planets would not exist. Human bodies would not exist. The chemistry of the universe would remain forever simple. Other first stars collapsed directly into black holes. If a star was massive enough, perhaps several hundred solar masses, its collapse created seeds for the supermassive black holes that later grew in galactic centers. Some of these black holes began pulling in matter immediately, forming the earliest quasars, objects so bright they can outshine an entire galaxy. Again, the brief lives of the first stars shaped not only the chemical future of the universe, but its gravitational structure too. The brevity of their lives also influenced the timing of cosmic evolution. Light from the first stars initiated ionization, but their deaths enriched and stirred the gas, allowing new generations of stars to form. These later generations, enriched with metals, cooled more efficiently and fractured into smaller masses. Their lifetimes grew longer. Their populations became more varied. The universe transitioned from a place dominated by brilliant but short-lived behemoths to a place populated by stars of every size, including small, long-lived stars like our Sun. When we look at the universe today, we see a cosmos shaped by these early fleeting giants. We see galaxies filled with complex chemistry. We see planetary systems forming from enriched gas. We see life emerging billions of years later from the carbon they created. In every way, these stars lived short lives, but left long shadows. Their brilliance, their instability, and their dramatic endings were not accidents, they were necessities. The first stars had to burn fast to reshape the cosmos quickly. They had to die young to seed the universe with the elements needed for depth, diversity, and complexity. Their lives were intense because they were the first to carry the burden of cosmic transformation. And as we drift gently into the aftermath of their luminous deaths, another question begins to glow quietly ahead of us. What elements did these first stars create, and how did those elements begin to build the universe we know today? Part 9. What elements did these first stars create? Inside their cores, the first stars forged new elements: carbon, oxygen, nitrogen, silicon, iron. Their supernovae scattered these atoms across space, mixing them into the cosmic gas. For the first time, the universe held the ingredients needed for planets, oceans, atmospheres, and eventually, for life. To understand what the first stars created and why their contributions were so transformative, we must drift inward, into the nuclear furnaces at their hearts, where gravity compressed matter so intensely that atoms fused into heavier and more complex forms. The early universe began with just 3 elements: hydrogen, helium, and a faint trace of lithium. That simplicity was profound, but it was also limiting. Without heavier elements, cooling was inefficient, dust could not form, and complex chemistry was impossible. The universe needed stars to enrich its material, to create the elements necessary for structure, stability, and life. And the first stars, enormous and short-lived, accomplished this task with remarkable speed. In the core of these massive giants, fusion began simply. Hydrogen nuclei fused into helium through the proton-proton chain, releasing energy and supporting the star's outward pressure. But as these first stars aged, and they aged quickly, their cores grew hotter and denser. Temperatures climbed to tens of millions of degrees, then hundreds of millions. In these extreme conditions, helium atoms fused into carbon. This process, known as the triple alpha reaction, requires extraordinary precision. 3 helium nuclei must collide within a tiny window of time. But in the blazing cores of population the 3 stars, this reaction unfolded continuously, producing the first abundant carbon in the cosmos. Once carbon appeared, a new pathway opened. At these temperatures, carbon acted like a gateway. It allowed the CNO cycle, carbon-nitrogen-oxygen fusion, to operate efficiently. In this cycle, Carbon serves as a catalyst, helping hydrogen nuclei fuse into helium while transmuting into nitrogen and oxygen along the way. This process didn't just produce energy. It began weaving a tapestry of elements, introducing chemical diversity where none had existed before. As hydrogen dwindled and the star shifted into helium-burning stages, the core contracted further, driving temperatures even higher. Carbon began to fuse with helium to form oxygen. Oxygen fused into neon. Neon fused into magnesium. Inside these massive stars, fusion proceeded like a slow but relentless march across the periodic table. With each step, heavier nuclei formed. The star climbed a nuclear ladder, rung by rung, from the simplest elements toward the more complex. Each stage required greater temperature and pressure, and each stage burned through its fuel faster than the last. In these final phases, shells of fusion formed within the star. Hydrogen burned in outer layers, helium burned beneath it. Deeper still, carbon fused, then oxygen, then silicon. The star resembled an onion, with each layer hosting a different nuclear process, and at the center, the star approached the limits of what fusion could accomplish. The silicon-burning phase, one of the last steps before collapse, produced iron. But iron is special. While lighter elements release energy when they fuse, iron absorbs energy. It cannot support the core against gravity, and so, when the core filled with iron, it became the star's downfall. Fusion ceased. Pressure could no longer counteract gravity. The core collapsed in an instant, triggering the explosive death of the star. And here, in this moment of collapse, a new kind of creation began. The temperatures and pressures during a supernova are not merely extreme, they are nearly beyond description. For a brief moment, the core becomes a furnace billions of degrees hot. Neutrons are produced in vast quantities. Atomic nuclei absorb these neutrons rapidly, forming new elements through a process called neutron capture. This is the realm of the R process, the rapid capture of neutrons that builds heavy elements far beyond iron. Gold, uranium, platinum, lanthanides, rare earth elements, and many others. Though early population 3, stars may not have contributed all of the universe's heavy elements, some of their most massive members likely underwent explosive processes capable of seeding the cosmos with at least some of these heavier species. Their supernovae enriched the primordial gas, transforming it from a simple mixture into a chemically complex medium. Imagine drifting through the remnants of such a supernova. You would find the once dark gas illuminated by shock waves of expanding debris. Carbon atoms would drift outward, cooling as they traveled. Oxygen atoms would mingle with hydrogen to form water in some distant future cloud. Silicon would condense into dust grains, tiny seeds that later helped new stars form. Iron would become the cores of terrestrial planets, and heavier elements, created fleetingly in the explosion, would someday find their way into rocks, oceans, and even living cells. These elements did not mix evenly at first. The enrichment happened in pockets, where supernovae detonated, where shock waves collided, where dense clouds captured the expelled material. Some regions became chemically rich sooner than others. These enriched clouds cooled more easily, allowing smaller stars to form. These smaller stars lived longer, creating the first stable, long-lived stellar populations. The ashes of the first stars changed everything. With metals now present, cooling pathways shifted dramatically. Gas clouds could dissipate heat more effectively, causing them to fragment into smaller pieces. Dust grains, microscopic particles of silicon, carbon, and oxygen, began to appear. Dust played a critical role. It shielded gas from radiation, catalyzed molecule formation, and served as the raw material for planets. For the first time, the universe had the infrastructure to support not just stars, but star systems. The chemistry of space became richer. Molecules such as carbon monoxide, water, and methane began to appear. These molecules influenced cooling, dynamics, and future star formation. And over time, as more generations of stars lived and died, the universe's chemical palette expanded further. The effects of these early enrichment processes echo through time. When we study meteorites in our own solar system, we find isotopes that originated in ancient supernovae. When we analyze the spectra of distant stars, we see signatures of elements made billions of years earlier in stars that lived fast and died violently. When we breathe oxygen or consume carbon, we hold remnants of stars that lived long before the sun formed. Every atom heavier than helium in your body came from the heart of a star. Every element that makes life possible was forged in a furnace hotter than imagination. The universe built complexity through the deaths of its earliest giants. And so the question of what the first stars created is inseparable from what the universe would later become. The heavy elements they produced became the architecture of galaxies, the chemistry of oceans, the minerals of planets, and the biochemistry of life. Their contributions were not merely chemical, they were foundational. As we drift forward from the brilliance of their creation and the violence of their endings, another question quietly emerges, shaped by gravity and collapse. What formed in the shadows of these explosions? What massive remnants did the first stars leave behind? Part 10. How did the first black holes form? Some of the earliest stars collapsed completely, leaving behind enormous black holes, much larger than what stars today can produce. These black holes grew quickly, feeding on gas and merging with one another. They may be the seeds of the supermassive black holes that now anchor galaxies. To understand how these ancient giants formed, we have to follow the story of the universe into its darker, quieter chapters, moments just after the deaths of the first stars. These stars, massive beyond anything familiar today, ended their lives in extreme ways. Some erupted in titanic supernovae, others collapsed entirely, leaving behind no explosion at all, only a point where gravity grew so strong that even light could not escape. These were the first black holes, silent and newly born in a cosmos that had only just begun learning how to illuminate itself. If you could drift near the site of one of these collapses, you would sense a profound stillness in the wake of its stellar death. A star that once shone with unimaginable brilliance would now be gone, replaced by a central region of intense gravity. Nothing visible marks the boundary of this new object. A black hole has no surface, no shell, no glow. Only its influence reveals its presence. Gas falls inward, space stretches, time itself bends. The fabric of the universe gives way to an object defined not by what it contains, but by what it no longer allows to escape. The key to forming these early black holes lies in the extraordinary mass of the first stars. Many population 3 stars weighed not tens but hundreds of times the mass of the Sun. Their immense size meant that their cores reached higher temperatures more quickly and burned fuel at rates far beyond what modern stars can sustain. When fusion ceased, when their cores filled with iron and could no longer produce energy, the support holding the star up against gravity vanished. The collapse was instant. The core contracted catastrophically, shrinking from the size of Earth to just a few tens of kilometers across. The outer layers fell inward as well. In some stars, this infall generated a blast so powerful that it tore the star apart in a supernova. But in the most massive stars, the collapse happened too quickly and too completely. The outer layers fell directly into the core, adding to its mass instead of rebounding in an explosion. The star simply imploded. The collapse was absolute, leaving behind a black hole hundreds of times the mass of the Sun. These early black holes were different from most black holes that form today. Modern stars rarely grow large enough to produce black holes above a few dozen solar masses. Stellar winds, magnetic fields, and metallicity changes limit their size. But the first stars had no metals to drive strong stellar winds. They retained their mass through their brief lives, and when they collapsed, they formed black holes on a scale that modern stars rarely achieve. Once formed, these black holes began to feed. The surrounding environment of the early universe was rich with gas, cooling clouds, ionized shells, and dense filaments woven by gravity. With no planets or mature galaxies to shape their surroundings, these black holes sat at the centers of turbulent clouds. As gas fell inward, it heated, forming an accretion disk that glowed with enormous energy. These feeding black holes may have been among the brightest objects in the early universe, shining not with their own light, but with the radiation produced by material spiraling into darkness. Some of these black holes grew rapidly, devouring gas at rates near the theoretical maximum known as the Eddington limit. When a black hole accretes too quickly, radiation pressure pushes material away, slowing growth. Yet, simulations suggest that the earliest black holes could bypass this limit under certain conditions, accreting gas dynamically, chaotically, and with little resistance. These super Eddington growth phases allowed them to balloon in size, doubling and redoubling over cosmic time. In regions where multiple massive stars had formed in proximity, their deaths could leave behind a cluster of black holes. Gravity drew these remnants together, allowing mergers that produced even more massive black holes. In the dense early universe, such mergers were far more common than today. The cosmic web was still forming. Gas and matter were clumped irregularly. Interactions were frequent. Black holes did not drift politely. They collided, spiraled together, and combined their masses in bursts of gravitational waves that rippled across the young universe. These merger events may have produced the earliest intermediate mass black holes, objects much larger than typical stellar remnants, but smaller than the supermassive giants found at galactic cores. Over hundreds of millions of years, these intermediate black holes continued to grow. Some settled at the centers of young galaxies, where gravity naturally pulled gas and stars into dense orbits. Once anchored in these central regions, the black holes had access to enormous reservoirs of gas. They fed, merged, fed again, and slowly transformed into the supermassive black holes we see today. By the time the universe was less than 1 billion years old, some black holes had already reached masses of 1 billion suns. Astronomers observe these early behemoths through the brilliant quasars they power, distant, luminous objects whose light has traveled for more than 13 billion years. The existence of such enormous black holes so early in cosmic history puzzled scientists for decades. How could anything grow so fast in such a short time? The answer lies here, in the lives and deaths of the first stars. Their immense size created the earliest heavy black hole seeds. Their deaths enriched the gas with metals, enabling more efficient cooling and faster star formation. Their remnants settled in dense regions where mergers were common, and their environment, crowded, turbulent, rich with gas, provided everything needed for rapid growth. These early black holes shaped the universe in subtle, far-reaching ways. Their accretion disks released radiation that warmed surrounding gas, influencing how nearby stars formed. Their gravity sculpted the centers of galaxies. Their mergers sent ripples through space-time, waves that modern detectors like LIGO and Virgo can now sense. The earliest black holes were not passive remnants, they were architects. If you could stand at the center of a young galaxy, you might feel their influence as a gentle distortion in the flow of matter. The stars would orbit in elongated paths. Gas clouds would spiral inward in smooth, glowing arcs. At the center would be a region of darkness, featureless, silent, yet shaping everything around it. A well with no bottom, a boundary with no surface, a first-generation black hole. The universe's earliest experiments in gravitational collapse. And as we leave these ancient shadows behind and drift toward the growing structure of the cosmos, one question naturally emerges. When did these young, enriched regions begin to gather into the first galaxies? Part 11. When did galaxies begin to form? With the first stars came gravity's new architecture. Clusters of glowing gas merged into growing islands of matter. These earliest galaxies were small, fragile, and chaotic, but they marked a turning point. The universe was no longer uniform. Structure had taken hold. To understand when galaxies began to form, we must drift back to an era when starlight had just begun piercing the cosmic darkness. The universe was only a few 100 million years old, young in cosmic terms, yet already filled with the momentum of enormous changes. The birth of the first stars did not merely illuminate space. Their gravity reshaped it, their radiation altered it, their deaths enriched it. Each of these effects nudged the cosmos toward the next great transition, the emergence of galaxies. Before galaxies, matter in the universe was spread across a vast, diffuse web. Dark matter had already formed the skeleton of this web. an invisible framework of filaments and nodes where gravity pooled matter more strongly. Normal gas following the contours of these dark matter structures drifted slowly inward. The earliest stars formed within these dark matter halos, creating tiny pockets of light suspended in enormous reservoirs of cold gas. These halos were small at first, only 1 million or so solar masses, minuscule compared to modern galaxies like the Milky Way, which weighs trillions of solar masses. But they were the first cradles of starlight, the earliest hints of what galaxies would become. Inside them, one or a handful of massive population 3 stars ignited, their ultraviolet radiation carving out ionized bubbles in the surrounding gas. Their gravitational pull bound the gas more tightly. Their supernovae stirred turbulence, heating and shaping the halo's internal structure. Every star that formed changed the halo that housed it, and every halo that hosted stars grew slowly more massive as gas and smaller clouds merged into it. Galaxy formation did not begin suddenly with one great event. Instead, it unfolded gradually, like the first threads of a tapestry being woven together. Small halos merged with one another, creating larger structures. Gas drifted inward along dark matter filaments, feeding these growing objects. Star formation flickered within them, sometimes accelerating, sometimes stalling, sometimes snuffed out by the feedback of massive stars. If you were drifting through space around 300 million years after the Big Bang, you would see a universe in the midst of this slow but steady transformation. The darkness that once filled every corner of space was growing thinner. In certain regions, particularly near large concentrations of dark matter, you would find small clusters of luminous points. These were the earliest protogalaxies, primitive assemblages of gas, dustless stars, and dark matter. They were nothing like the grand spirals and ellipses we see today. They lacked structure, stability, and symmetry. Many were lopsided clouds rather than well-defined systems. They formed stars rapidly, then lost gas suddenly due to the intense radiation and winds of massive stars. Entire protogalaxies could be blown apart by a single pair instability supernova, scattering their metals into the intergalactic medium. But even when shattered, their fragments did not disperse completely. Gravity remained patient, clumps reunited, new halos formed, star formation resumed. This chaotic assembly was crucial. It seeded the universe with chemical diversity and taught gas how to cool more efficiently. Once metals from the first stars permeated the gas, cooling became dramatically easier. Gas clouds fragmented into smaller pieces, forming longer-lived stars. Star formation rates increased, and protogalaxies could finally stabilize enough to begin forming identifiable structures. By around 400 to 500 million years after the Big Bang, the universe had hundreds of thousands of these small galaxies. Most were only a few percent the size of today's Milky Way, but they represented the first building blocks of galactic architecture. Gravity drew them toward one another, causing frequent collisions. Unlike the catastrophic collisions of modern galaxies, filled with dense stars and complex structure, these early mergers were softer, quieter, more fluid. They involved clouds of gas colliding, mixing, and igniting new waves of star formation. Inside these merging halos, something remarkable began to emerge. Disks of rotating gas, supported by angular momentum inherited from tidal interactions. These disks formed the earliest foundations of galactic rotation. They were fragile and easily perturbed, but they revealed a cosmic truth that would shape all future structure. Galaxies were beginning to acquire spin. Eventually, as halos grew more massive, reaching tens or hundreds of millions of solar masses, they could retain gas even in the face of powerful stellar feedback. Their star formation became more continuous rather than episodic. Radiation still heated gas, but gravity now had enough strength to pull it back inward. This tug-of-war between feedback and collapse created a balance that allowed galaxies to grow steadily. By around 700 million years after the Big Bang, the first recognizable dwarf galaxies existed. These systems contained thousands to millions of stars, many of which were second-generation stars enriched by earlier supernovae. Their chemical fingerprints, visible today in ancient stars, reveal a gradual shift from simple hydrogen and helium to mixtures of carbon, oxygen, magnesium, and iron. These galaxies were still small, but they were stable. They survived feedback. They formed stars progressively. They developed gravitational cores dominated by dark matter. They were galaxies in their adolescence, growing quickly and shaped by every interaction. As the universe approached its first billion years, the galaxies grew larger, brighter, and more diverse. Some became compact starburst galaxies, small, dense systems with intense star formation. Others developed more tenuous, irregular structures. A few grew massive enough to begin acquiring shapes resembling young spirals or spheroids. Many formed central black holes that siphoned gas and released enormous energy, further influencing galactic evolution. We now observe some of these early galaxies with the James Webb Space Telescope. Their light has been stretched and dimmed by cosmic expansion, traveling more than 13 billion years to reach us. And yet, even in their youth, these galaxies exhibit unexpected levels of complexity. Some are brighter than models predicted. Some contain more stars than they should at such young ages. These discoveries reveal that galaxy formation began early and progressed rapidly. The earliest galaxies also played a crucial role in finishing cosmic ionization. Their combined ultraviolet radiation ionized the intergalactic medium, clearing away the last remnants of the cosmic fog. This process made the universe transparent to shorter wavelengths of light and allowed starlight to travel freely across vast distances. Galaxies were not only structures within the universe, they were engines of cosmic transformation. As we drift through this era in our imagination, we see a universe changing from darkness to brilliance, from uniformity to structure, from simplicity to complexity. Galaxy formation was not an isolated event. It was the outcome of millions of small interactions, gravity's slow pull, the violent feedback of early stars, the merging of halos, the cooling of enriched gas, and the shaping influence of dark matter. These small galaxies would continue merging for billions of years, eventually assembling into the grand systems we know today. The Milky Way itself grew from hundreds of such proto-galaxies, each one a spark born from the earliest cosmic light. And as galaxies emerged from darkness, another question naturally rises, whispering through the expanding filaments of the cosmic web. How did the heat and radiance of these first stars begin to change the temperature of the cosmos itself? Part 12. How did starlight change the temperature of the cosmos? The heat from the first stars warmed the surrounding gas, slowing further star formation. This feedback created a delicate balance, light as both a sculptor and a barrier. The warmth from early stellar generations determined where the next generation of stars could rise. To understand how profoundly starlight influenced the temperature of the cosmos, imagine drifting through the universe just after the first stars ignited. Until this moment, the cosmic gas had cooled gradually since the Big Bang, dropping from thousands of degrees to mere tens. The universe was cold, quiet, and dark. And then, suddenly, enormous stars appeared, radiating ultraviolet light, stellar winds, and intense thermal energy into the fragile medium around them. The birth of these stars marked not just an end of darkness, but the beginning of a subtle and ongoing thermal transformation. The first stars, massive and brilliant, poured energy into their surroundings. Their radiation ionized hydrogen, stripping electrons from atoms. This process alone heated the gas significantly, pushing temperatures upward by thousands of degrees. The ionized gas became more energized, moving more quickly, and resisting gravitational collapse. The effect was immediate and long-lasting. Dense regions close to early stars could not cool efficiently, making it harder for them to form new stars. This was the first form of cosmic thermal feedback. Starlight, in essence, decided where the next stars could appear. If you were drifting near one of these newly shining giants, you would sense a shift in the cosmic environment, an invisible warmth radiating outward, spreading across light years. The once cold hydrogen fog would now tremble with subtle heat. In these regions, star formation would slow, Gas clouds that had been preparing to collapse might stall, their internal temperatures rising just enough to stop gravity from tightening its grip. But the story wasn't that simple. While the first stars heated their immediate surroundings, they also sent shockwaves outward, shells of gas that compressed more distant clouds. Compression increased density. Higher density made cooling more efficient. In these more distant regions, gas clouds could collapse faster. Starlight therefore played a dual role. It delayed star formation close to its source while triggering new stars farther away. Cosmic heating was not destruction, it was reorganization. This balance between suppression and stimulation is one of the key evolutionary processes that shaped the earliest galaxies. In the towering heat of early starlight, star formation became self-regulating. Too much light and gas heated, escaping small halos. Too little light, and clouds collapsed uncontrollably, creating unstable bursts of star formation. The earliest galaxies survived by learning to distribute heat in complex, dynamic ways. One of the most dramatic shifts came from photoheating, the process by which ultraviolet photons heated gas after stripping its electrons. The ionized bubbles around early stars reached temperatures of about 10,000 Kelvin, far hotter than the cold gas between galaxies. This temperature difference created pressure gradients that pushed matter outward. Small dark matter halos, those with shallow gravitational wells, lost much of their gas. Their star formation shut down. Only larger halos retained gas, becoming the cradles of more stable star formation. In this way, starlight determined which halos grew into galaxies and which remained dark. But starlight worked on grander scales too. As more stars formed across the early universe, their combined radiation heated the intergalactic medium, the vast stretches of gas between forming galaxies. The average temperature of cosmic gas rose steadily, first to hundreds of degrees, then to thousands, then to more than 10,000. When reionization swept through the universe, the gas everywhere became ionized, heated, and energized. The cosmic temperature map changed dramatically. This heating slowed down the formation of dwarf galaxies, which struggled to accumulate and cool gas in the new, warmer environment. Larger galaxies continued to grow, but the smallest halos, those that might have become faint star clusters, never formed. Their potential stars never lit. Their gas remained too warm to fall inward. In this way, starlight shaped not only the structure of galaxies, but also the population of galaxies themselves. The warm intergalactic medium acted as a filter, allowing only sufficiently large halos to form new stars. This phenomenon helps explain why the universe today has far fewer dwarf galaxies than simple models of gravity predict. Many of those small halos simply lost their gas long before they could shine. But the changes caused by starlight did not end with reionization. As the first generations of stars died, they seeded the cosmos with metals: carbon, oxygen, silicon. These metals drastically altered the thermodynamics of gas clouds. They allowed gas to cool more efficiently, fragment more readily, and form lower-mass stars. These new stars emitted less ultraviolet radiation, creating a softer, gentler form of cosmic heating. Star formation became more stable, less explosive, and more sustained. The universe transitioned from an era dominated by enormous, short-lived giants to an era ruled by smaller, longer-lived stars, stars like our Sun. But the memory of the first star's heat remained woven into the structure of galaxies. Their thermal influence controlled when galaxies formed, how quickly they grew, and what kinds of stars they could produce. Over time, galaxy clusters formed in the densest regions. Their gravitational pull trapped hot gas, building reservoirs that remain heated even today. Astronomers observe this heat through X-ray emissions, signatures of gas heated to millions of degrees, a process that began with the earliest generations of stars. Even now, starlight continues to regulate temperature. Massive stars heat their surroundings with stellar winds and radiation. Supernovae inject heat and turbulence into galactic gas. Black holes, those formed from the earliest stars, release enormous amounts of energy as they feed, heating gas on scales far larger than individual galaxies. Starlight, across cosmic time, has been a thermostat, raising temperatures when necessary, cooling them indirectly through metal production and shaping the cosmic landscape one photon at a time. If you could watch this process unfold from a quiet vantage point, it would look like a cosmic interplay of fire and shadow. Regions glow, warm, expand, then cool, collapse, and ignite again. The universe breathes, thermally speaking, in and out, heating, cooling, forming stars, stopping stars, all in a delicate cycle millions of years long. The heat from the first stars was not a brief spark. It was the first act in a long symphony, one that continues to shape the universe's evolution even today. And as we drift from the warmth of early starlight toward the discoveries of our modern era, another question emerges softly from the ancient glow. What has the James Webb Space Telescope revealed about these first luminous giants? Part 13. What does JWST reveal about these first stars? The James Webb Space Telescope is now peering back toward the dawn of time, capturing galaxies from just a few 100 million years after the Big Bang. Their faint red-shifted light carries hints of enormous ancient stars, revealing a universe already glowing earlier than many scientists expected. To understand how extraordinary this is, imagine drifting through time itself. The farther JWST looks, the younger the universe becomes. Light from these distant galaxies has traveled for more than 13 billion years, stretched and softened by the expansion of space. What reaches the telescope today is not bright or sharp. It's faint, fragile, stretched into the infrared, like a whisper carrying messages across the vastness of cosmic history. And yet, within these whispers lie clues that are reshaping our understanding of the first stars. When JWST first opened its golden mirrors to the sky, astronomers expected to see early galaxies, small, dim, primitive systems just beginning to form their first generations of stars. But what they found was far more surprising. Some of these early galaxies were bright, some were massive, some looked chemically evolved. Their light carried signatures of surprisingly complex stellar populations, and woven through that light were hints of something even more remarkable: the influence of the first giant metal-poor stars. Because the first stars themselves are impossible to see directly, they lived fast, died young, and left no visible remnants, we must find them through their fingerprints. These fingerprints take the form of unusual spectral lines, ionization levels, and color patterns in the galaxies they influenced. And JWST is extraordinarily sensitive to these clues. With its infrared vision, it can observe wavelengths that carry the earliest stories of starlight. One of the most striking clues JWST is uncovering is the presence of extraordinarily bright and blue galaxies at very high redshifts, galaxies that existed just 300 to 500 million years after the Big Bang. Their brightness suggests something unusual about their stars. They may have been hotter, more massive, and more energetic than typical stars today. In other words, they may have been shaped by, or still contain, population 3 stars. Population 3 stars, the very first stars, would have been enormous and metal-free. Their spectra would show almost no absorption lines from heavy elements. Their radiation would be intense, dominated by ultraviolet light, and while we cannot see them directly, their presence would affect the entire galaxy around them. It would ionize gas, alter emission lines, and create specific colors in the galaxy's light. JWST has found galaxies whose signatures match these expectations, galaxies that shine brighter than they should given their estimated mass, galaxies with unusual color ratios, galaxies that appear too luminous for their size. These anomalies suggest that the earliest stars may have been more common and perhaps more extreme than we once believed. Another hint comes from the spectral fingerprints of early galaxies. JWST has captured emission lines from hydrogen and helium that point to incredibly hot stellar populations. One of the most tantalizing signatures is the potential presence of P2 1640 angstrom emission, a hallmark of very hot metal-free stars. While not yet confirmed in every candidate, its appearance in some early galaxies has electrified astronomers. If validated, these signals would provide the first indirect evidence of population 3 stars, stars that lived billions of years before our sun and forged the universe's first heavy elements. JWST also reveals that many early galaxies contain more stars than expected. Their stellar masses appear high relative to their age. In some cases, galaxies seem too mature, too bright, too chemically enriched to have formed so early, unless the first stars accelerated chemical evolution more quickly than previously believed. This suggests that early star formation may have been ferociously efficient. The first giants may have enriched their surroundings rapidly, allowing multiple generations of stars to form in quick succession. This early brilliance challenges models that predicted a slow rise in galactic growth. Instead, JWST hints at a universe that wasted no time, a universe where gravity was eager, gas was abundant, and the first stars ignited cosmic evolution with startling speed. Another revelation comes from the shapes and sizes of early galaxies. JWST images show tiny, compact galaxies packed with stars, dense clusters glowing intensely in wavelengths our eyes cannot see. Some galaxies appear clumpy, irregular, or stretched by interactions and mergers. These chaotic shapes support the idea that early galaxy formation was turbulent. The first stars were not merely forming, they were influencing everything around them, shaping gas flows, triggering new star births, and sometimes disrupting their fragile host galaxies entirely. JWST also captures hints of early black hole growth. Some of the brightest early galaxies show signs of active galactic nuclei, supermassive black holes consuming gas at the centers of young galaxies. Their existence so early in cosmic history suggests that the first black holes, formed from the collapse of massive population 3 stars, grew rapidly. This rapid growth would require enormous amounts of gas and chaotic early environments, conditions JWST is indeed observing. Even the colors of these early galaxies tell a story. Many emit strong ultraviolet radiation, indicating the presence of star clusters forming stars at intense rates. Some show surprisingly little dust, consistent with young, unenriched systems. Others show dust earlier than expected, suggesting that early supernovae enriched the universe quickly. JWST's infrared view allows us to detect this dust that could only form from the explosions of massive stars. This dust may mark the graves of the very first giants. Taken together, spectra, brightness, structure, dust content, and chemical fingerprints, JWST's observations paint a picture of a cosmos that ignited rapidly. The earliest stars may have been abundant, massive, luminous, and short-lived, shaping galaxies in ways we are only now beginning to grasp. They raised temperatures, they enriched gas, they seeded black holes, they sculpted the universe before galaxies even had stable shapes. And the deeper JWST looks, the more it surprises us. It shows us that the early universe was not slow or simple. It was dynamic. It was restless. It was filled with brilliant stars that changed everything in cosmic moments. It shows us a universe that came alive earlier than expected. And as we drift gently through these discoveries, each one a new window into the distant past, another question begins to appear, quiet but profound. What mysteries still lie beyond JWST's reach in the dark spaces before even the first stars were born? Part 14. Why is it so hard to see the first stars directly? The earliest stars lived fast and died long before their light reached us. Their galaxies were faint, distant, and tiny. What we detect today are their consequences: the warmed gas, the enriched elements, the altered patterns in cosmic background radiation. We see their fingerprints, not their faces. To understand why these ancient giants remain hidden, we must drift back across the universe's vast timeline, all the way to the era they inhabited. These stars lived more than 13 billion years ago, in a universe that was radically different from the one we observe today. Space was smaller. Matter was denser. Light had a harder time traveling through the thick fog of neutral hydrogen that filled every corner of the cosmos. The universe had not yet become transparent to ultraviolet radiation, and the first stars existed in a time when darkness still dominated. Their light had to navigate an environment that was not yet ready to let it through. The difficulty begins with distance itself. Light from the earliest stars has traveled for almost the entire history of the universe. As space expanded, that light stretched. Once energetic ultraviolet photons became long-wavelength infrared photons. Once brilliant radiation dimmed into soft whispers, barely distinguishable from background noise. The first stars were massive and bright, but their light was swallowed by cosmic time and expansion. By the time it reaches us, it is faint beyond measure, buried beneath the glow of everything that formed afterward. But distance and expansion are only part of the challenge. The first stars were born inside tiny dark matter halos, structures so small and faint that even the James Webb Space Telescope struggles to detect them. These halos contained very few stars. A typical early halo might have produced only one or two massive population 3 stars. Even if we could see the halo itself, the light from those stars would be so diluted, so mixed with gas and emerging dust, that it would be nearly impossible to distinguish one star from the collective glow. Moreover, the lifetimes of these first stars were astonishingly short. A massive population 3 star might live for only 2 or 3 million years, a blink on cosmic scales. The galaxies that hosted them needed millions more years to grow bright enough to be seen across cosmic distances. By the time a forming galaxy became luminous enough for us to detect it, its first stars had already died. Their light had already faded. Their supernovae had already enriched the surrounding gas. What remains is not the star itself, but the aftermath. Another difficulty comes from the cosmic medium of the early universe. Before reionization, the cosmos was filled with neutral hydrogen. Neutral hydrogen absorbs ultraviolet light extremely well. The first stars emitted intense ultraviolet radiation, but the universe was not yet transparent. Their light was absorbed almost immediately by the surrounding fog, reprocessed into longer wavelengths, and scattered in every direction. Very little escaped. Even after reionization began, most early star-forming regions remained buried inside dense clouds of gas. The first galaxies were chaotic, dusty, and turbulent. Massive stars lived and died so quickly that their explosions filled their small host galaxies with debris. This dust absorbed light from later generations of stars, making the galaxies dimmer and more complex to interpret. The intergalactic medium added yet another challenge. As the first stars ionized the gas around them, they created bubbles of transparency. But between these bubbles were long stretches of neutral hydrogen that absorbed nearly all light shorter than a certain wavelength. This absorption produced the Gunn-Peterson trough, a signature of a universe not yet fully transparent. It also erased much of the earliest ultraviolet light that could have revealed the first stars directly. Even the tools we have today, extraordinary telescopes built at the edge of our engineering abilities, are limited by these cosmic conditions. The James Webb Space Telescope can detect galaxies from only a few 100 million years after the Big Bang. But even JWST must rely on indirect signatures to infer the presence of population 3 stars, unusually blue colors, extreme ionization levels, and chemical fingerprints that suggest a lack of metals. These clues hint at the existence of early giants, but they do not show the stars themselves. Part of the difficulty is resolution. A single early star is far too small to resolve in a galaxy that might be tens of billions of light-years away in comoving distance. Even a cluster of early stars is unresolved at these scales. We see only the integrated light, the collective brightness of all the stars, gas, and dust combined. A population 3 star, even if it were incredibly luminous, would be lost in the glow of its environment. Another subtle challenge comes from timing. The earliest stars formed in tiny halos at around 100 to 200 million years after the Big Bang. But JWST's earliest detections, currently around redshift 14 to 16, correspond to around 250 to 300 million years after the Big Bang. That missing window, where the first stars lived and died, remains just beyond our current observational reach. We can infer what happened, but we cannot yet see it directly. Even gravitational lensing, one of our most powerful tools for magnifying distant galaxies, faces limitations. Lensing can amplify light from early galaxies, but the magnification depends on chance alignments with massive foreground clusters. And even when lensing works, The structures we see remain unresolved smears of ancient starlight, not distinct stars. And yet, despite all of this, the universe leaves behind unmistakable evidence of its first luminous inhabitants. We see their influence in the abundance of certain elements in ancient stars within the Milky Way. Chemical fingerprints pointing to population 3, supernovae. We see their impact in the temperature of the intergalactic medium. We see their effect in the timing and structure of reionization. We see hints of their brilliance in the unusually intense ultraviolet emission of early galaxies. What we observe is a universe already transformed by these ancient giants. Their absence is a sign of their presence, and perhaps this is the quiet truth. The first stars were never meant to be seen directly. They were catalysts, they were teachers, they were cosmic architects. Their purpose was to ignite the universe, enrich it, and fade long before the galaxies they shaped became visible across cosmic time. But the story doesn't end here. As we drift deeper into this cosmic history, one final question emerges softly, the last piece of this quiet puzzle. What remains hidden in the darkness before the first stars formed, and how close are we to finally seeing it? Part 15. How did the universe transition from darkness to light? The end of the cosmic dark ages was not a moment, but a slow brightening. One star ignited, then another, then whole clusters. The fog thinned, the temperature shifted, the chemistry changed. In time, the universe became transparent, illuminated, and ready for the galaxies we see today. To understand this transition, the quiet rise from darkness into radiance, we must drift into an era unlike any other in cosmic history. After the Big Bang, the universe cooled, expanded, and entered a long twilight. For nearly 200 million years, nothing shone. Hydrogen atoms floated in a cooling fog, unbroken by spark or flare. The universe was calm, vast, and almost perfectly dark. But beneath this calm, gravity was slowly gathering the material that would initiate the first flickers of light. This transition began with small fluctuations, tiny overdensities left imprinted on space from primordial quantum variations. These slight irregularities acted as seeds. Over time, gravity amplified them. Regions slightly denser than average grew even denser as gas drifted inward. These pockets of collapsing gas would become the birthplaces of the first stars. But the process was slow. The universe had to cool enough for hydrogen atoms to clump together, but not so much that collapse stalled entirely. It took hundreds of millions of years for the conditions to align. And then, quietly, the universe crossed a threshold. One region collapsed a little faster, then another. Inside those collapsing clouds, hydrogen atoms, compressed, heated, and eventually fused. The first stars ignited, massive, brilliant, and short-lived. These giants illuminated the darkness with searing ultraviolet light, carving small, transparent bubbles into the cosmic fog. These bubbles were not luminous in the way we think of brightness today. They were regions where neutral hydrogen had become ionized, where light could finally pass unobstructed. Around each star, a sphere of clarity spread outward, an island of transparency in an ocean of shadow. The transition from darkness to light unfolded as these bubbles grew and merged. Each bubble represented the influence of a massive star or star cluster. When many stars formed in the same region, their ionized bubbles overlapped, creating larger and larger windows of transparency. And as early galaxies began forming, their combined radiation accelerated the process. Star formation became more efficient, more clusters ignited, more light flooded the surrounding gas. Still, this was not a sudden dawn. It was a slow lift, a gradual thinning. The cosmic fog, neutral hydrogen spread across billions of light years, absorbed ultraviolet light eagerly. For a star's light to escape, it had to ionize the hydrogen around it, clearing a path. This took time. In some regions, the fog resisted. In others, new stars formed faster than the gas could recombine. These differences created a patchwork universe, a cosmic quilt of dark regions and glowing islands. Ionization was a process of transformation, not just illumination. As the first stars ionized hydrogen, They changed the chemistry of the universe. Electrons detached from atoms, turning neutral hydrogen into a charged plasma. This plasma became transparent to ultraviolet light. Meanwhile, starlight heated the gas, increasing its temperature by orders of magnitude. This heating slowed the formation of new stars in the smallest halos, but accelerated it in larger ones. It created pressure gradients, carved out voids, and influenced the distribution of matter on vast scales. The early supernovae of these stars enriched the surrounding gas with heavy elements. Carbon, oxygen, silicon, and iron spread outward, allowing gas clouds to cool more efficiently. This cooling enabled the formation of smaller, longer-lived stars. Dust appeared for the first time, tiny grains forged in the explosions of ancient giants. Dust scattered and absorbed light, driving further complexity into the transition. The universe was learning how to create light more efficiently. As galaxies grew, their combined ultraviolet radiation formed networks of expanding ionized bubbles. These bubbles were not random. They followed the underlying structure of the cosmic web. Dense filaments ignited first, lighting up early galaxies strung like beads along invisible dark matter threads. Vast voids, low in density, remained dark longer. Slowly, the patches of darkness shrank while the glowing regions expanded. Eventually, after hundreds of millions of years of starlight eroding the fog, these bubbles merged into a single, interconnected structure. The cosmic web lit up. Light could travel freely for the first time across enormous distances. Ionization reached its tipping point. Darkness did not vanish completely, but it loosened its hold. The universe had crossed into transparency. This moment, the end of the cosmic dark ages, marked the birth of cosmic visibility. It shaped everything we observe today. Galaxies could grow more massive. Light could escape their boundaries. Black holes could influence their surroundings on larger scales. Star formation began accelerating in complex cycles. The cosmic background radiation remained, but its patterns now evolved under the influence of new heating and new structures carved by gravity and light. The universe became not only bright, but dynamic. As the fog thinned, photons that had once struggled to travel even a fraction of a light year could now move across billions. The night sky, once empty, became filled with pinpricks of light, though from our vantage point today, many of those ancient lights have long since died. Still, their glow continues to travel. Light became a storyteller. It carried the history of early galaxies across time. It carried the fingerprints of the first stars. It carried the clues that JWST now deciphers at the edge of the observable universe. Even the faintest redshifted signals from this era carry the memory of the moment the universe transitioned from darkness to brilliance. This transformation from dark to light was also a transformation from simplicity to complexity. In a dark universe, only hydrogen and helium existed. After the first stars, metals appeared, molecules formed, dust grains crystallized, galaxies took shape, planetary systems became possible. Biology, eventually, had the raw materials it needed. The universe we inhabit, a universe filled with life, structure, and meaning, became possible the moment starlight began reshaping the cosmic canvas. And as we drift quietly through this long arc of transition, from the earliest photons to the rich galaxies of today, one final reflection arises softly from the distant past. Light did not simply illuminate the universe, it awakened it. It warmed the cold, it structured the chaos, it seeded the chemistry of life. It gave the cosmos a language, a memory, and a future. And in that slow brightening, the universe took its first steps toward everything we now see, everything we now know, and everything we now are.